Yay!
Yay! All right, we already know that linear momentum can be conserved. It's always conserved. And so one of our other grand principles of physics is that angular momentum is always conserved. So let's look at an example of that. Now that we know how to compute angular momentum. What happens if we have, we'll take the case of a star because something like this actually happens. What if we have a star that collapses? Normally stars are sort of kept inflated by the nuclear reactions at the center, right? Producing all the energy. But at the end of a star's life, let's just suppose the nuclear reactions stop. And so the star can't stay inflated anymore, and just through the action of gravity, it starts collapsing. So let's say I've got a star with initial mass m and initial radius r, I, there on the left. And as when it collapses down to a final object that's got a r final. It's got the same mass. Let's just, to make things simple, let's suppose it doesn't lose any mass. So it's the same amount of mass. It's just more dense. It's just smaller. All right. And further, what we're going to say is that this thing is rotating, like the sun. The sun rotates. Well, what's going to happen? You've seen this before. If you see like an ice skater pulling his or her arms in, the rate of rotation goes up, right? You're sort of condensing all the mass closer to the axis of rotation, and the person speeds up. The rate of rotation speeds up. That's called conservation of angular momentum. Here's where it comes from. What we're going to say, if something is conserved, remember what that means is that the initial equals the final. Okay, so let's write down what the initial is. The initial angular momentum is just I omega. So I omega must be I final omega final. Okay, so this means I can solve for my final angular rotation rate. This is just going to be I initial over I final times omega initial. Okay, no problem. What we're going to say is that our final, I'll write it like this. How about this? Our initial is 100 times our final. It's going to collapse by a factor of 100, let's say. So more or less, it's something the size of the sun collapsing down to something the size of the Earth. That object, by the way, is called a white dwarf. More or less, that's what happens at the end of a star like the sun, the end of the lifetime of the sun. It doesn't retain all of its mass, but just really roughly, that's sort of what happens. So if the sun is already spinning, omega I is equal to the sun's rate of rotation, the period, oops, I better write it like this. The period of rotation, Ti, is about, let's say, 25 days. All right. What we want is not the period. What we want is the angular rotation rate in radians per second, right? That's what omega is. So we need to convert. So we'll use the conversion that we've done before, which is omega is 2 pi over t. So if you do that, what you find out is that omega is, if you plug in your numbers, it was something, what did I get? Something like 2.9 times 10 to the minus 6 radians per second. Okay, whatever. So that's the initial rotation rate of the sun, if its period is 25 days. Okay, so we're going to find the final. So omega final is I initial. Okay, what is the moment of inertia of the sun? Let's suppose, this is not true, but it's just an approximation. Let's suppose the sun is a solid ball. So the sun is 2/5 mr initial squared, right? That's the I initial. The I final, it's also a solid ball with the same mass, but now I've got an RF down there. Okay, so notice the mass doesn't even really matter. The 2/5 are going to cancel. So it's just a ratio, the squared ratio of the radiuses. Okay, so I can do this. So omega final is just going to be, let's see, Ri, this was 100 Rf squared over Rf squared, omega I, right? Okay, well, the Rf is going to cancel then. So this is going to be 100 squared times, all right, so that's like 10,000. So the rotation rate goes up by a factor of 10,000. It's squared. It's it's a square of the ratios of the radii, the sizes before and after. So the rotation rate goes up by a factor of 10,000. That's a lot. So if something originally had a period of 25 days, what's the new period? Well, if you take that thing and multiply it by 10,000 and then convert it back to minutes, that's kind of boring, so I'll let you do it because you like to do the boring stuff. So T final, if you multiply by 10,000, turn it back into minutes, you should get something. What did I get? You should get something like 3.5 minutes. Okay, so this thing is really spinning fast now. Where it was 25 days, now it's only about 3.5 minutes. Very cool. So all we did was just conserve angular momentum. The initial is going to be equal to the final. What's changed? The moment of inertia has changed. The I has changed. So if the I changes, then the omega's got to change to compensate. So what happens to a figure skater? You bring your arms in. If you're skating, you have decreased your I, right? Initially, your arms are far out. Let me make sure I'm getting the camera. Initially, the arms are far out, and then you bring them in tight. So you're putting more mass. I is mr squared, right? You're decreasing that r. So you're making your moment of inertia smaller. If you make the moment of inertia smaller, if this number, if I goes down, then omega's got to go up because the product has to stay the same, right? That makes sense. All right. Oh, here's where people get in trouble. Here's the most common student mistake that I see. Is that sometimes you forget what needs to be conserved, and you're used to conserving energy. This is a new thing that's conserved. What about, here's what a lot of people try to do. What about rotational kinetic energy? Here's what people try to do. They try to conserve rotational kinetic energy. They try to say that 1/2 I omega squared, because that's the rotational kinetic energy, stays the same, right? It doesn't. Let's show that. Let's show that that's true. Let's compute. I'm going to change this just a little bit. Let's compute the final. This is the final kinetic energy. Let's compare it. Oops. Let's compare it to the initial kinetic energy, I initial, omega initial squared. I mean, if kinetic energy is conserved, then those two things ought to be equal, and we'll get a fraction that's 1, right? But that's not going to happen. Watch this. So that's 1/2. Those factors go away. This is written as I final, omega final times omega final, right? I can kind of factor out the omega f. And this is I omega times, oops, plus, not plus, times omega initial. Okay, what is conserved is angular momentum. So this piece is the same as that piece. So I can cross those out, right, just by conservation of angular momentum. And then I just have these two, omega final over omega initial. But we already said that omega final is 10,000 times omega initial. So this is 10,000, right? So the final kinetic energy is 10,000 times greater than the initial kinetic energy. So kinetic energy is for sure not conserved. You might ask, where the heck did all that energy come from? Well, it came from the gravitational potential energy, right? Out here, before the thing collapses, you have all these little bits of mass here in the sphere, all having some gravitational potential, and they all fall towards the center. They lose gravitational potential, it gets turned into kinetic energy. In this case, kinetic energy of spin. So don't do this. Do not conserve rotational kinetic energy because it's not conserved. Total energy is conserved, but the kinetic energy is not conserved. If you checked kinetic and potential, you'd find that they are conserved. But people try to conserve kinetic rotational, and it just doesn't work.